Heder very well, of course, because he was studying here a long time ago. and then she pursued her PhD in Australia. Then she got a postdoc position in South Africa, first time in, not at this university. Yeah, with Waterstan University. And then she moved to Johannesburg, and now she works at the University of Pretoria, and she just got her permanent position. So, and then it's a pleasure for me and for all of us to have you here to share your knowledge. Thank you.
Thank you, Pak Hendra. So for those of you maybe know, Pak Hendra was my undergraduate thesis, tugas akhir, undergraduate thesis advisor. So it's good to be back, and thank you, Pak Hendra, for inviting me to speak. I actually got introduced to this area because of my undergraduate thesis. So it's been a long journey, but I will try to take you through this journey and what I've learned so far. But first of all, I would also like to thank well, they're not here, but I would like to mention this, my colleagues at the University of Pretoria. So before coming here, I gave a series of presentation there just to make sure that it's running smoothly here. So I got feedback from them, and I hope this will be better than what I gave in Pretoria. Okay, so you can see from the title, the topic is called semi-inner products, so it should have something to do with inner products, right? But why is it different, and why people are looking at this? So let's see. I'll try to introduce a few things. Okay, so you all have the handouts, right? Yeah. So my idea was just outline. So if you want to just write things down, please go along with me. Okay, so what is nice about inner product space? Well, you can define really nice things, right, in the inner product space. So you can, you see earlier Mikio-san's picture of, you have something like this. That's vector 1, 1, right, and then you project off a boundary, right? This is the basic proposal. So you have orthogonality. How does it define? Well, if you have inner product, then it's easy. X is orthogonal to Y, if and only if your inner products, right? Easy. Okay. Hendra alluded to this yesterday. If you have inner product, you can also define angle between two vectors. So let's say you have a vector like this. That's your angle theta. Then cos theta is what? Xy divided by under vectors. Okay, so nice. Another thing is risk representation there. So this is quite easy to state for any bounded linear functional. Yeah, bounded, very simple. You have a vector space over R, say. That's your functional. Bounded simply means that there exists an M such that you have something like this, yeah? Okay, so for any bounded linear functional, bounded and continuous in this sense is the same. On X, well, Rodman likes to call it F. On X, there exists some X in its original space, right? Such that you can write that functional, you can represent it with inner products, right? So it's quite nice. Okay, and here X depends on F uniquely, and the norm is the same. Okay, so it's quite nice. Yeah, Hendra used this yesterday without mentioning.
Risk representation.
Risk representation here. Talk about the supremum and etc. etc. Okay, thank you. So that's risk representation there, right? Okay. Now, You all know this, I feel like, but I want to show it anyway. So what are the axioms for inner products, right? So I may need this later, so I'm just going to write this. So I'm just going to write the properties, right? So X is the vector space. My vector spaces are all over R. You have a mapping from X plus X to R, and it's an inner product if it satisfies the following property. Property 1 is linearity. We all know this. And property 2 is homogeneity, right? So if I multiply with alpha, I can take the alpha out, essentially, right? What's happening? Number 3 is symmetry. And number 4 is positive definiteness. So if you take inner product of X with itself, it's always non-negative. It's 0. If and only if X is 0. Right. Okay. Yeah. And from this thing, if I take half, over half, then I get a norm, right? This is what we know from functional analysis or linear algebra, whatever wherever you saw it it's from. But norm itself actually has the following axioms, right? So first is that norm of X is always, so none is the mapping from X to R, so it depends on one vector. Property 1, similar to that last one, right? That 4. If you write it as half, so it's similar, right? Okay, so you have that norm of X is non-negative, and norm of X is 0 if and only if the vector is 0. Homogeneity sort of pops out with an absolute value, and we have triangle inequality, which you saw already from MYSAGA. Okay, but here, if you look at it, well, there's no inner product or anything like this, right? So, and in fact, this is true, right? Every time you have an inner product space, then you do the following, then you get a norm, right? But if I have a norm, it's not necessarily an inner product induced norm. Okay. So, if you have an inner product space, it must be a norm space, but the converse is not always true. And it's true if you have the norm satisfy the parallelogram law, which looks like that. We all know this. And example of something that is not inner product space, inner product induced norm is the little LP norm. I have to say what P is. P is between 1 and infinity. I need restriction, which you will see in just a moment. So if you have the LP norm, it looks like this, right? This is in R2. Right? So you have IXY, absolute value of X to the P, plus absolute value of Y to the P. You take the P's power. If you consider 1, 0, and 0, 1, you just quickly make your calculation. You want to check if your parallelogram identity holds or not, right? So you look at the left-hand side, you look at the right-hand side. Left-hand side, after some calculation, you can check this later. I'm just going to skip this. Your X is 1, 0, your Y is 0, 1. You'll get 2 to the power 2 over P plus 1. Right-hand side, if it is correct, it should be, if they're equal, it should be equal to 2 to the power 2, right? And you can see that these two things are equal only when P is equal to 2, right? So when you make P not equal to 2, then you don't get parallelogram identity. So LP for P not equal to 2, they are not inner product, not induced norms. Okay, so the question is the following. Suppose I want to have some inner product-like structure, but I'm not in an inner product space. What do I do? Or can I do something, right? So that's the question. So can we have an inner product-like structure in any given norm space? If we have, then perhaps, we can sort of transfer this information like orthogonality, like bridge representation theorem, or whatever geometrical properties, right? Perhaps. But of course with limitation, right? We know that inner product space is very nice, normal space not so nice. So the answer to this question is, well, yes we can, but also they don't behave so nicely, this inner product-like structure. In fact, the nicer the geometry of the normal space, and I'm thankful that Professor Kato spoke before me, so he already introduced most of the geometrical properties. Yeah, so the nicer the geometry, the nicer the structures. So this, we will see what this is in just a moment. This inner product-like thing in your normal space will behave better, depends on the geometry of the normal space. Okay, so now, then we come to semi-inner products. Okay, so suppose you have a vector space X. So here I didn't say anything about norm, I didn't say anything about inner product, I'm just introducing a new structure. Yeah. So I have my vector space is X over the field R, and I use square brackets to denote, to distinguish. Whenever you see this, I mean inner product. Whenever you see square brackets, I mean semi-inner product. Yeah? Okay. So the mapping, again, is similar to inner product, right? X cross X goes to R. It's called semi-inner product if it satisfies the following properties. Okay, I wrote the one for inner product. Let's compare them slowly. Okay. So, number one, you have linearity. Oh, similar, right? I'm just changing my angle brackets to square brackets. Nothing funny, everything's still fine. Okay. Number two, same thing. I have alpha multiplied with X. The alpha pops out, right? Okay. Here when it gets a little bit different. Number three, I have to state the following. You will see why in just a moment. So 3 and 2 basically similar in some sense, right? Only I multiply with alpha with y instead. And again, the alpha pops out. Just a note, if this is complex, then you need to conjugate. Yeah. Right. And then you have following. This is positive definiteness again, similarly to that one. Okay, so number 4 looks the same again. Right? Okay, so seems like I'm skipping something, right? I'm skipping this one. There's no symmetry written in the axiom. Hence, the idea for number 3. Right? So homogeneity holds for the first argument and the second argument, but not additivity. So if you're talking about linearity, it only works for the first argument. That's the ugliness to this one. Okay. So only near the first argument. Homogeneity kind of holds for the second one. No symmetry. So this is not true. I will give an example. In general, this is not true. Yeah. Okay. And I need to add one more axiom, which is very important here. And this is because, well, you see it yesterday, you saw it yesterday already. This is kind of like Cauchy sorts, right? Well, not quite. In Cauchy sorts you have inner product, and over here you have norm. Right? Okay, this is almost like Cauchy sorts. Okay, so this is important, and unlike in inner product space, Cauchy sort is implied by their axioms, but here Cauchy sort needs to be added to the axioms. Okay, and you can guess this already. What happens if I do this? Will I get a norm? Well, the answer is yes. If not, then this is a horrible story, right? Again, so if you do similarly like in the construction of inner product, you take semi-inner product of X with itself, take the square root, again, you will get a norm. Okay. So 3 things to prove for norm. Number 1 is what? We have positive definiteness, right? So if you write inner product xx square root become your norm, it should follow from S4, right? So I'm gonna skip that one, fairly easy. Then you multiply with alpha times x, you take norm. You can combine a few of these axioms, you will get again similar, alpha pops out with absolute value. And as Hendra said yesterday, the difficult one is always triangle inequality. So let me prove that one. Okay, so triangle inequality, and you will see now why that axiom number 5, it needs to be there. Okay, so to prove triangle inequality, my notation is N3, property N3 in my note. Okay, so take x, y, and x, arbitrary. If x plus y is 0, then easy, right? Because norm of x plus y will be 0, and always. This is true. Okay, so we don't consider it. Very simple. So if x plus y is not 0, then what do? Well, I need to combine a few of my axioms. Okay, I'm going to do the following. X plus y squared is what? Well, I rub off my definition already. Right? I can write it as semi-inner product of x plus y, but be careful. Your linearity only holds for the first argument. So x plus y, x plus y, right? Okay, and then you apply axiom number 5. Well, this is actually inner product xx if I follow axiom number 5 with a square root, right? But now I can rewrite it as norm of x. Now it looks like Cauchy swaps, right? Okay, so then you do the same thing, x plus y, do the same thing here, norm of y, norm of x plus y. You can factorize norm of x plus y out, then you get norm of x plus norm of y. Our assumption is that x plus y is not 0, right? So this norm is not 0, so we can cancel both sides. What do you get? Triangle inequality. So the behavior is kind of like what Hendra said yesterday. A triangle inequality usually follows from Cauchy source inequality. So this is essential to be in the axiom. Okay. All right. So what are we doing here? Essentially, we say that every semi-inner product space is a norm space. This is true for inner products, right? I just delete my S. We know this. But we know that for inner product, that way is not true. Magically, I can change this to if and only if. So every norm space is also a semi-inner product space. Okay, so that's the nice part. Meaning what? Meaning if I have just any norm space, right? And I would like some sort of inner product, I can use semi-inner product. Okay. So the proof for this one is a little bit more tricky, but it's okay. Let's go through it slowly. Okay, so one side, we are done. With this. But let's prove the other side of the implication. Okay, so what we want to prove now is if I have a semi-inner product space, if I have a norm space, can I construct a semi-inner product? Or just in existence, in fact. That's fine. Okay, so where's my zero? There you go. Let x be a vector. No, not that one. That one we proved already. This. I start with a norm space. Can I find an inner product space? So statement goes, if x is a norm space, then there exists a semi-inner product which generates the norm on x. Generates the norm, this means if you do the construction again, xx, you raise it to the power half, then you get its original norm. That's what it means, yeah? Okay, so we need my second note. for this one, Hanbana theorem. Okay, so let me just state Hanbana theorem very quickly. There are many versions of Hanbana theorem, but the one that I'm using is for norm space. Okay, so what does it say? I have a norm space X. Yeah, and I have a subspace in there. If F is, so this notation Y star essentially just means that F is a bounded linear functional on Y. Then there exists capital F on X star such that if you evaluate capital F only on the subspace Y, you get that function again, right? So the restriction recovers your original functional, and norm of F is equal to norm of del F. Okay, so I'm going to use it. Right, so Hanbana theorem essentially to say if I have some functional, some bounded linear functional on the subspace of X, then I can extend this, right, to its entire space with the following property, right? That the norm of these two guys are the same. Okay, so proof not of Hanbana, but proof of that theorem. Okay, so we're going to use Hanbana theorem. So for all X, my notation is the same with Professor Kato's notation, as X is just a collection of vectors in X that has norm 1. Okay, so for all unit vectors in X, there exists a functional in X star such that Fx is equal to 1. Essentially what's happening here is you apply Hanbana theorem, where Y is just the span of one vector, right? And you choose in such a way that this is F evaluates to 1. Okay, so that's what you do. So this is from Hanbana. Existence follows from Hanbana. May not be unique, but doesn't matter. We just choose one if it's not unique. So we have this kind of thing, and because my F depends on X, I'm going to put little subscript of X. Okay, and for what happens if my X is not in unit sphere, so let's say I multiply with lambda. Again, you apply Hanbana theorem, span the vector X, evaluate to lambda times the previous. So again, there exists F in X star such that F lambda X, so now because it depends on lambda X, I'm going to put my subscript lambda X. This is equal to lambda times Fx, which is from the previous case. Okay, so I'm choosing all these functionals, and then I define my candidate for my semi-inner product, my X, to be the following. Okay, so this is for all X. X. You can check very quickly, is this a semi-inner product? Okay, so we have, first of all, if I do XX, what's going to happen? I have Fx. X, remember here, X can be anything, right? So why don't we write it like this? F norm of X, multiply with X divided by norm of X, and you do the same thing. X divided by norm of X, right? So this is now a unit vector, this is now a unit vector, right? So I can use the knowledge from here. First of all, this norm of X is a scalar. This is a linear functional, so that guy can pop out. Yeah? Secondly, this guy is again a scalar, and I have this property, right? So my lambda, which is again norm of X, can pop out. And now I have F, let me just write X hat. Now X hat is a unit vector, and this guy is 1, so I get X squared. Check, property 1. Okay, you do the same thing with, I'm going to combine my homogeneity to one thing. Right? So how to write this? So I'm again following how I set it up. Right? So f beta y alpha x. Same argument like before, linearity, and my choice of second functional, alpha pops out, beta pops out. I get fyx, which is actually yx, as I set it up in the beginning. Oh, sorry. This should be xy. My apologies. You will see later on why I swapped it. It's something to do with my second construction. Doesn't matter. My apologies. Sorry to confuse you. Okay, so this is what we have. And then what else do we need to check? Linearity, but only for the first argument. Right. You can see this already. So if I follow this, what happened? My index will be z. Right? My subscript will be z, and then I have x plus y. Linearity of the functional fzx and zy. Then you rewrite it again, you get xz and yz. Right. And finally, Cauchy-Schwarz, xy is equal to fxy less than or equal to, I hope you know this already.
Oh, you got it implicitly. fyx.
Sorry, I wrote this again. It's very confusing, these things. Here you have what? Fx, fy, no. Fy and then x, right? Oops, it's not the x. Okay. That's the operating norm. Okay. And then this is what? I'm going to claim. What is happening? Yeah, this is fine. And you can check quickly that this guy will be equal to normal y. Why is that? Well, let me do it here. So if I have fy, this is f of y, again that trick that I did earlier. Yeah. And then this is equal to what? Norm of y. So this guy pops out, right? Like from the second one, and then it's positive, so I take it out without changing anything, and then now I have something that is of norm 1. Right? Okay, so I get y. Okay, so I get my Cauchy-Schwarz. Okay, done. Sorry, this thing is very confusing, mixing the where's the y and where's the x. But thank you for the corrections. Okay. Alright, so we have this theorem. So it says that this is nice, right? Unlike inner product space, now we have the reverse implication. You start with a semi-inner product space, you can generate a norm. But if you have a norm space, you can find semi-inner product that generates back the original norm that we start with. Okay. Now, theorem marks. I said this, every norm space can be represented as a semi-inner product space. So the idea is, okay, now we can replace everywhere you see inner product. Let's try to replace it with semi-inner product, right? So for example, if you have orthogonality, you have usually x orthogonal to y, if and only if their inner product is 0. Now you just replace it with semi-inner product. But be careful. Why? This is not necessarily guaranteed, right? So you can't say two things are orthogonal. You have to be careful here. You can say x is orthogonal to y, but y may not be orthogonal to x. Right? So we have to be extra careful here because of form. And losing the symmetry actually makes things really complicated. Okay, so we will see in the next few days how complicated they can get. But it's not all bleak. Sometimes when the spaces are nice, you can get really nice results. So let's see further with this comment number number 4. Okay. So, since this is a mid-year school, I will give homework. So, exercise. Check that this is a semi-inner product. So just check all the axioms, right? You can combine 2 and 3 together. Just so it's only check 4 instead of checking 5. Okay, so if you have R2 with little L1 norm, in case you forget, let me just say xy, because we are in R2. L1 is what? Just sum of their absolute values, yeah? Okay. So, if that is your norm, you can show that this is it's a semi-inner product. Okay. Be careful with a and the. The means that's the only one. This is not necessarily the only one. Okay. So this is a semi-inner product that generates the L1 norm back. How does it look like? Xy is norm of y, multiply with. This is the sine function. Easy, yeah? So if it's negative, then it's -1, 0, 0, positive 1. Sine y1 x1 plus sine y2 x2. Okay. So this is a semi-inner product in Bill L1. Homework for you. This is a school. Okay. And note for the semi-inner product given up there, if you select these 2 guys, if you look at like -2, 1 and 1, 1, let's just punch it in here, right? So the semi-inner product of this is what? So first of all, norm of y, this is y, is 2, right? And then sine of y1, positive, multiply with x1. Did I get this right? Yeah. Yeah, this is right. No, it should be, yeah, this is correct. So we have, let's write it somewhere here, replace the Banach theorem. This is correct, I think. So the norm is 2, norm of y, right? And then sine of y1 is positive, x1 is -2, so we get -2, plus sine of y2 is positive, times x2, is again 1. So 2 times -1 is -2, yeah? But if I reverse it, so let's calculate this. Norm of this, norm y, right, is 3. And then sine y1 times x1 is -1 plus sine y2 times x2 is 1. What do I get? 0. Not equal, yeah? So symmetry is not necessarily guaranteed. So suppose I define my orthogonality just to say x orthogonal to y if semi-inner product of x, y is 0, then you see that this guy is orthogonal to that, but not the other way around. Right? So symmetry is not guaranteed. So it's not very nice because semi-inner product is nice, you can just change slope, whatever you like, but not with semi-inner product. You have to be extra careful. Hence the name semi. Right. Okay. So over the next few days, the 3 things that I mentioned in the beginning, we will look at carefully. How does orthogonality look like? Can we improve certain things? When the space is nice, maybe we get nicer orthogonality. We will talk about this. Okay. And Riesz representation theorem, which I mentioned in the beginning. Do we still have Riesz representation theorem? So that's again the question, right? Can we still get Riesz representation theorem? Spoiler alert, only in some nice spaces. And what is these nice spaces? One of the things that already mentioned by Professor Kato earlier, you will need at least uniform convexity. But you will need something else. Okay, and then angles. How to define angle and how are we going to, what can we do with it? Okay, so I'll talk about this tomorrow. I'll talk about this on day 3. With angles, I will talk about it over 2 days. So that will be day 4 and day 5. And in semi-inner prospects. But so far, right, I haven't talked about how do I construct a semi-inner product space, right? All I say is that there exists a semi-inner product space. And in the L1 case, I gave you what it is, right? But if I started with a norm, can I construct it? Because then it will be nicer, right? But every time you have a norm, you can construct your semi-inner product, and then you can do things, right? You can actually compute a semi-inner product. Well, as the theorem that we proved earlier only says about existence. There exists a semi-inner product. Okay. So the question is, can we construct one given a norm? Okay, the answer is almost. Not very nice. Okay, so we'll see. Alright, so lemma, I have the following. I don't think I have the time to prove it, it doesn't matter. I'll just mention sort of the idea of it. Okay. So let X be a normal space. These functionals, the claim is this always exists for all x, y, and x. Okay. What is this functional? So the way you construct this is you take the norm of x plus ty minus the norm of x, you divide by t, and then you take the limit as t goes to 0 from the left and from the right. Okay. So this kind of looks like directional derivative in some sense, right? This is called the Kato derivative, left side and right side, depending on where you take 0 from. So the proof, I'll just give you some hint how to prove this. The proof is following. Let me just say sketch of proof. All you need to show is that given x0 in x for all y in x, the following function, the following mapping from t to x0 plus ty minus x0 divided by t from r take away 0 r is non-decreasing. You will use the fact that norm is convex function in order to show this. I probably will write down the proof and send it to the final slide. And once you know this, then if you take the following, look at the following set, t positive, and again similar set, t negative, because this is non-decreasing, if I take the infimum of this and supremum of this, they exist, and this will be in fact the limit of that whole thing as t goes to 0 from the right, and limit of that whole thing as t goes from 0 from the front, goes to 0 from the right. Okay, so the idea is once you can show that this is non-decreasing, then you're done. It's a fun exercise concerning the convexity of the norm. Okay. And with this functional, you can play around with it, right? Just assume you start with something that you already know. Inner products. Okay. Then again, it's an exercise. I'll give you a hint of how to show this, this thing. You basically just look at the function ft, which is equal to norm of x plus ty, inner product space. So you can rewrite this as norm of x squared plus 2t, inner product xy plus t squared, y squared, everything to the power half, right? You take the derivative with respect to t, you will get, here left, right is the same thing, and you will get that the derivative at 0 will be exactness. So use that, and you will get that tangent functionals, as we call it, they're the same from the left and from the right, and it is equal to xy divided by norm of x. Of course, because we're dividing the norm of x, I give a restriction that x is not 0. So just try it. If you get that identity. Okay, so that means we have the following, right? We have the following identity, that the tangent functional xy is this guy divided by x, or if I rewrite it, inner product xy is equal to norm of x times tangent functional xy. Now if I don't have this, right? Because this Kato derivative, left from the right, Not always the same, depending on the norm. In inner product space case, they're the same thing, right? I can actually get this again by doing the following. Let me just say, yeah, this doesn't matter. In inner product space, this is true. Tau negative xy is tau positive xy divided by 2. Okay. So this will serve as the idea of how to construct a semi-inner product, right? So you get inner product by doing this, right? So the idea for semi-inner product will be almost the same, right? So you have these tangent functionals, you take the arithmetic mean of the left one and the right one, you multiply with the normal limits. We call this guy G. And this is introduced by Milicic, Serbian mathematician, and it looks like this. Okay, so G of xy is norm of x, tau negative xy, tau positive xy divided by 2. Okay, and this we claim to be our potential candidate for our semi-inner product. Okay, so let's see what the properties of G and xy, of G is. Number 1, if I take G of xx, I get norm of x squared. Oh, this is exactly what we want, right? Okay. So property of semi-inner product. The first one, check. Second one, if I multiply x with alpha, y with beta, again, these alpha beta can pop out. Also nice. I like this. Number 3. Okay. Here's where you see the reason of why I'm swapping things around. X plus y is gxx plus gxy. So linearity almost only happens on the second argument instead of the first one. Doesn't matter. If I have linearity, I'll just swap it around. So hence you understand why I was confused here, because I usually work with G instead of the brackets. Okay. But be careful here. Not only it says that quote-unquote linearity happens in the second argument, but here we have x plus y, not x plus y and z. Yeah? So these two things have some relationship in some sense. Yeah? So it only works the following way. Okay. Number 4, you get Cauchy watch, which is nice. So our problem is really only that number 3. Right. Okay. So let's see. 1 more minute. Okay. It's okay. I probably just won't prove it. Exercise proves G1 to G2. Okay. Now, when the two tangent functionals are equal, we say that the norm space is smooth. This may be not exactly definition in some textbook, but some textbook also use this definition. It doesn't matter. So whenever we talk about smoothness, this is what I mean. So if you just want to look at a picture of your unit sphere, so if I have L1, unit sphere looks like this, right? Like a diamond. L2 is nice and round. Smooth essentially means that I have, at every point, I don't have corners like these guys. Yeah? So those are my non-smooth points. So little L1 is not a smooth norm, L2 is a smooth norm. Okay, whenever you see these corners, they're not smooth. Okay. Like absolute value function, eh? Not differentiable, right? And that's 0, 0. Okay, so that's sort of the similar idea. Okay, now, if you impose the condition that your norm space is smooth, then you get linearity in the second argument. So then, you generate your semi-inner product just by swapping the x and y with the g, right? So you start with the g. If your space is smooth, then you have linearity. You swap it. This is your semi-inner product. Okay. So already here you see what do we need? Smoothness. Okay. All right. So that is that, and I will just give you 2 more examples, and I can close. My plan initially is to prove this, but it doesn't matter. I can just give you some hints to prove it. Okay. So in L2, sorry. How does the semi-inner product look like? If x is 0, is 0. If x is not 0, this is how it looks like. Okay. So norm of x, power 2 minus p, and then inside this summation, you have norm of x, sorry, absolute value of xi raised to p minus 1, sine xi yi. Okay. So this I say for P between 1 and infinity. This is a semi-inner product. Okay. But if I substitute P equals 1, what happens? So here I only have norm of x. Here I have 0, so this guy disappeared. And I get again that sign xi, yi. Kind of like the little L1 that I gave you earlier. Right? Okay, the difference is, well, the x was y, the y was x. And it's only in R2. This is for infinite sequences. Okay? So this, when you are in LP, it's not only just semi-inner product, it's a semi-inner product, it's the unique semi-inner product. Okay. However, so this is semi-inner product. Even though L1 is not a smooth space because of that picture, right? You can still get a semi-inner product. Yeah? So smoothness ensure you that if you use that G, you will get a semi-inner product. But sometimes you can also have semi-inner product constructed with that G, even though the space is not smooth. Okay. In that case, we will call it the norm space to be G type, capital G, perhaps inspired by this G. Okay. So if in my previous formula, this one, I substitute P equals 1, then I will get this, and this is a semi-inner product on little L1. Okay, even though the space is not smooth. Okay. So you can, again, homework, so many homeworks. Check with that tau whatever to get this formula with little LP. Just use the definition of little LP. It's actually not so difficult. And you will use chain rule here and there. It's not so difficult. Nice multivariable calculus exercise. Okay. Yeah, and just to rehash again that here, even though the space is not smooth, we can still use this G sometimes. In fact, little L1 is correct. Okay, I think I'll stop here. Thank you very much.